So in this video, we'll be going over a problem that's very similar to what we've dealt with earlier. Before, we dealt with this same sort of setup with two masses on a board that's being balanced, and we were asked to determine what the unknown mass should be. For there to be rotational equilibrium, that means that the sum of the torques must be zero. So rotational equilibrium, sum of the torques must equal zero. So before, it wasn't too hard to figure out what the unknown mass was because we have our pivot point here. We know the distance to the known mass, which is the same distance on the opposite side of the pivot point to the unknown mass. And so those masses needed to be the same. And so the unknown mass needed to be 5 kilograms. But now this problem switched up. Now we don't have a massless board. And so we have to take into account the center of mass of the board that the masses are sitting on. And so since that center of mass is not located at the pivot point, that changes our problem because that force, the weight of the board, will cause a rotation about the pivot point, which means that there is a torque as a result of the weight force of the board. So let's take a look at the situation. Let's draw our forces and determine what our torques are. So the first thing you want to do is define your coordinate system. I'm going to choose up to be the positive y direction, to the right to be the positive x direction, and a counterclockwise rotation to be positive. So now labeling our forces. From the first block, we have a weight force downwards, W1. That's equal to M1 times G. For the second block, we don't know what the mass is, but that's a weight force 2, and that's equal to M2 times G. And that's ultimately one of the things we're looking for. We know that the board has a weight force of 90 newtons, and that is pointing downwards. So I'm going to call that WB is equal to 90 newtons. Question is, where is that located? So we're given that each marking on the board is half a meter. You can deduce that by how far the first block is from the pivot point. And so we have 8 blocks. Divide that in half, that would be 4 blocks. And so you find that from the pivot point, the weight center of mass of the board is 1 block away from the pivot point to the right. We have one more force that we need to worry about, and that will help balance out these forces since we know that this is in equilibrium, and that is the force from the pivot point being pointed upwards. And that's one of the other quantities that we are asked to solve for. So now we can label our distances. I've already mentioned to the first block that is equal to 1 meter. And then to the center of mass of the board, that's equal to half a meter. And then from that point, another half a meter to the second block. So at this point, we've drawn our forces and we've labeled all of our information. Now let's take a look and see about the pivot point, what forces will these torques cause? Will they be a counterclockwise rotation or a clockwise rotation? So let's take a look at that. So about pivot point, let's look at the weight force due to the first block, and let's see what kind of rotation that wants to cause. That wants to cause a counterclockwise rotation going this way. So the torque as a result of this weight force will be positive. What about the force from the pivot point? Well, that is located at the pivot point, so we know that the torque about that is 0. Any force acting at your pivot point will not produce a torque. Moving on to the weight force of the board, that is also pointing downwards, but it's to the right of the pivot point, so that's going to want to cause a clockwise rotation, and that will be a negative torque. And then for the torque due to the weight force of mass of block 2, that will cause a torque in the same direction, and that will also be negative. The other thing to note is that the forces here, the weight forces, are all going to be perpendicular to the distance from the pivot point. And so the angle between those two vectors, the force vector and the distance from the pivot point vector, are going to be 90 degrees. So let's come down here and draw an FBD for our system, which is the board. We have 4 forces that we need to account for. We have the weight force of the board. We have the weight force due to mass 1 of block 1. We have the weight force due to block 2. These are in equilibrium, so these need to be balanced out by an upwards force, and that upward force is a result of the force due to the pivot point. You can almost think of this as a normal force. So planning our solution, we know that in equilibrium, we have rotational equilibrium, which means that the sum of the torques must sum to 0, since those tend to cause a rotation. And then if we're not accelerating, then the sum of the forces must be 0 as well. We know that the torque is equal to the force times the distance from the force to the pivot point multiplied by the sine of the angle between the force vector and the distance vector. For our case, F and R are perpendicular to each other, so sine of 90 degrees is equal to 1. So we're just left with the force times the distance from the pivot point to those forces. So let's go ahead and implement this. We're going to start by summing the torques. We've already figured out what the direction of those torques are based on our coordinate system, so that makes life a whole lot easier when determining the sine. So now we just need to pull off what we just found up top down here. So we have the torque due to the first block is positive, and then the torque due to the board's weight and the weight of the second block are negative. Substituting all of that in, we have 5 kilograms for mass 1 times g times 1 meter minus the weight due to the board, 90 newtons times 0.5 meters, minus m2 times g times 1 meter equals 0. Plugging that in your calculator, you find 4 Newton meters is equal to the mass of the second block times 9.8 meters per second squared, leaving you with a mass of the second block of 0.41 kilograms, which is significantly less than what we found earlier when we dealt with the board that was massless. Now that we've found the mass, we need to determine what the force at the pivot point is. There we sum the forces to 0 since we are in equilibrium. we have only one upward force, which is the pivot point, and then the weight forces are pointing downwards. Moving the pivot point to one side, we are left with 49 newtons plus 90 newtons plus 4.018 newtons, leaving us with a force at the pivot point of 143 newtons upwards.